I'm David Sanders. I'm going to talk about how to compute 1 million stationary points in a second. And to do this, we'll be using the GPU. Let's remind ourselves that a root of a function is a value of x such that f of x equals 0. And f here is a function from Rn to Rn. The case that I want to be looking at is finding the stationary points of this so-called Grievank function that I've written here. And the stationary points satisfy that the gradient of g is 0. In other words, that the function is flat at that point. As standard numerical methods cannot ever guarantee to find all of the roots. So how can we actually do this? So here's a picture of the function, and I've plotted points at each of the local maxima, local minima, and saddle points here. So how can we actually find all of those roots of this gradient function? The way we're going to do that is using interval arithmetic. I've talked about this at a few previous talks at JuliaCon. I'm just going to summarize it here. Basically, what we would like to do is to calculate the range of a function f over an input set x. That's the set of all possible values that f can take. The way that we can actually calculate this in a computationally cheap way is using interval arithmetic. So we're going to work with intervals x, which are all real numbers between a and b, and represented by the endpoints a and b of the interval. And then we're going to define arithmetic operations such that f of x, where f is a function and x is an interval, is going to compute a set, an interval that encloses or contains the true range of the function. It often will be an overestimate, but it definitely contains the true range. So here's an example. We're going to define a standard Julia function f of x, x squared minus x minus 1. And we'll define an interval 3 to 4. So this is all real numbers between 3 and 4. And then we can apply this function f to the interval x. And what it will do is compute this set 4 to 12 that's guaranteed to contain the true range of the function. So how can we use this? Well, what we can do with it is actually find a region where there is no root. Because if 0 is not contained in this interval evaluation of the function over the set, then 0 cannot be in the actual true range of the function. So here's an example, the same function f, the same interval x. We can just ask Julia, is 0 in f of x in the interval evaluation? And it is not. And so we know that there is actually no root of the function in that set. So how can we now find all roots? Well, we're going to do that by splitting up the set, splitting up the domain. So here we're going to start with a new interval minus 3 to 4, and then we will mince that. In other words, we'll split that into 10 equal sized intervals. And this is what the result looks like. So what we're doing here is plotting each interval on the x-axis and the output on the y-axis, the output of this interval evaluation of the function. Here's the actual function that we're using, the same function as before. And what you can see is that most of these boxes, the output range does not contain 0. And so we know that there is no root inside those boxes. The two boxes that are colored blue are the only ones that actually contain 0. And so they are the only positions where there might be a root of this function. So clearly, this process is actually highly parallelizable because each box is independent. And in each box, I need to do this check of is 0 in the range of the function over that input. So GPUs have thousands of cores that compute in parallel, that compute at the same time. We want to run the same calculation, this particular calculation of checking whether 0 is in the range, with different data on all cores or processors simultaneously. And we're going to call each piece of work a thread. So now, how can we actually use the GPU? We're going to use this fantastic package CUDA.jl, and we're going to actually create an array on the GPU just by calling this cuArray constructor, and that will copy over the data from the CPU, which is in this vector v, to the GPU and create a new vector v2 that lives on the GPU. And you'll notice that this vector actually contains these interval objects. This is a user-defined type that we defined in the package, but it now is actually creating objects of that type on the GPU, or at least that's how we can think of them as programmers. It's useful to point out that a few other languages actually allow you to use user-defined types in this way. And so Julia is actually enabling us to use the GPU with a higher level of abstraction. And the easiest way to actually then use this is with vectorizing the operation using broadcast. So here I'm applying this function that I defined. I'm applying it element-wise to this GPU vector, this vector that lives on the GPU. And it is applying that function. And so it's actually compiling that function for the GPU and applying it element by element and creating a new vector on the GPU. So for example, what I can do is say, I want to do this element-wise check if 0 is in the image of each element of the images f applied to each interval in the vector v2. And that's going to give me this mask, which is an array of booleans that also lives on the GPU. The intervals of interest are the ones that give ones in this mask vector. And so we want to actually filter out those intervals that cannot contain a root, that are the zeros here. And it's just not obvious how to do this in parallel. This was sort of the major stumbling block of applying this algorithm on the GPU. So how can we actually do this parallel filtering? We're given a vector v and a Boolean mask, and we're going to call a thread successful if its position in the mask has a 1. So we want to just extract those elements that are successful. And normally we would write this using logical indexing as v square brackets mask. So we need to work out how to do this on the GPU. And what we actually need is to know the position in the new array to which each successful thread will actually write. And the way we did this is by using the cum_sum or cumulative sum function. So here's the mask again. And now here is the cumulative sum of the mask, and you'll see that each time we have a 1, of course, the value of this cumulative sum increases by 1. And so it gives a unique position for each element which has a 1 in the original vector. And so a successful thread with index I is going to write to the slot or position in the new array given by pos square brackets I. And that's actually now implemented in a Boolean get index on a GPU array as follows, and it returns the correct thing. So once we have that piece in place, we can now run the entire algorithm, which is called a branch and prune algorithm, where we repeat the following steps. We're going to take these intervals and bisect them, divide them into 2 pieces, double the number of intervals, and then apply this f dot of v to calculate the images and remove the ones that cannot contain zeros. And then we also have another step where we need to prove that a box does contain a root, and to do that we use an interval version of the Newton algorithm, which is called the Kravchik method. So what are the results? We can actually find and verify just over 10 to the 6, 1 million stationary points in a particular box of this Grievank function. We're using forwarddiff.jl for automatic differentiation to calculate the gradient. And the timings are that it takes 240 seconds on one CPU core, and it takes 1 second to do this entire calculation, verifying these 1 million roots on an NVIDIA GPU which has just over 5,000 cores. So this is a new benchmark problem, and we believe a new record for calculating roots of functions. So in conclusion, we have implemented this generic vectorized branch and prune algorithm that works on CPU and GPU with absolutely no code changes, and with this pretty nice speed up even before optimizations. Thanks for your attention.